All right, so this is section 4.5 on page 233 is where it starts. The title is Linearization and Newton's Method. With what I'm going to cut out of it, it should be titled Linearization and an Introduction to Differentials. That should be what it's titled, okay? Linearization, big word, what's the root? Linear. Even better than that. Line. Isn't that what we've been studying with derivatives? Derivatives gives us slopes to tangent lines. And whatever value on the function that we draw a tangent line, that point on the function gives us enough. We have a point, and the derivative allows us to find the slope, which just allows us to write the equation of a line, that tangent line, right? We know from algebra that this is the equation. When it says write the equation of a line, that's how the instruction begins. I tried to teach you and hammer it into your head that this is the form of the line you should use. It's called the point slope form, right? And it requires what to write it? Slope and a point. And I told you in calculus where we get those. It's the point on the curve, whatever the curve is that we wish to draw a tangent line. That's the point. And the slope is determined by the derivative of the curve evaluated at the x value of that point. That sound right? Okay, so with that in mind, watch how this evolves into what's at the bottom of the page on page 233, which at first glance, when you look at it, you go, what in the world? When you see it evolve, what you're familiar with evolve into that. It's not going to be that unfamiliar. Be okay. So watch. If I if I start out like this, that would be okay, I think. Right? That'd be all right? Okay. If I do this, this is the big leap. Would that be okay? Y1, and we're talking about evaluated at A, and I didn't tell you that. X equals A. Okay. Then Y1, meaning the Y coordinate of the point, is F of A. That's a Y value at A when X is A. Plus the slope, but in calculus, the slope for the line at X equals A is F prime of A. You with me there? And then X1, that's the X coordinate of the point, becomes A when I'm calculating this for A, right? Yeah. And so we'll just make one more change, and we'll call this Y value L of A, meaning the linearization at X equals A. The Y value that we would get for it's called a linearization at A. That's the Y value. It's L of A. If this is A right here, then this is L of A. This is the X. This is the Y. The Y is going to be called L of A. I hope you grab onto that. It's going to be F of A plus F prime of A times X minus A. Did you see that evolution? Did you follow that? Look at the bottom of the page. It says that very thing. It shouldn't say L of A though. It should say L of X. Sorry, this is itself a function of X, but it's a linear function of X. So if this is X right here, see right up here, if this is X here and this is the Y that goes with it, then if this is the X here and this is just some arbitrary value of X, this is the Y that goes with it, whatever you choose. So these go together. This is X and Y. This is X and L of X. And we're evaluating at a point on the function F at A. And you may be looking at that and going, okay, yeah, I kind of buy that, I guess. But what? So now comes the history part. Historically, people didn't have these graphing calculators that could find derivatives at a point in a fraction of amount of time. They had to figure it for themselves. And the equations of lines and plugging things into lines was way easier than plugging them into, say, a trig function, which required a lot of graphing and a lot of knowledge and a lot of tables that they had to put together. They had to go look things up on tables, or they had to figure it out for themselves. Trig functions is an example. Exponential functions is another. If you wanted to evaluate it at a decimal, it's tough to do, but it's really easy to plug something into a line. And so if you were willing to take a little tiny bit of error, you could use a line to approximate it by linearizing the function at a particular point and using the line to evaluate things. What I mean is, if I've got a curve like this, comes out like that, and I wish to know what the value is, I don't know, this isn't working out like great, but if I wish to know what the value of this function is at this point right here, we'll just call it x, but I know what the tangent line is right here, then I could plug this x into that tangent line and find an approximate value for this that's awfully close. This is called the center point, and as long as we don't deviate too far from it, we can use the tangent line at that point, which is often easier to write here than here. If we use the tangent line at that point and plug it into the line itself with the equation of the line, this x value that we want to know, get us a good estimate. It's really close, as long as we stay close to the point of center, the center point. That's the idea behind linearizing things, because these are far easier to plug things into than the function itself most of the time. So let me show you how it's going to be used. You can even do some arithmetic with it and get a really close approximation of different things. I'll show you. Okay, so that's our linearization. And the center of approximation is the point AF of it. All right, example 1 says, find the linearization of this function. F of x equals the square root of 1 plus x. Here's the function. This would be a difficult thing to evaluate, for example, using some sort of square root algorithm without a calculator at, say, if x was 0.02. That'd be tough, because you would be trying to square root 1.02. But that's a hard thing to do, even if you have an algorithm, because of the decimals involved and stuff like that. So here's what we're going to do. We're going to use the calculus to find a really good approximation of the square root of 1.02 by linearizing f at x equals, I'm sorry, when y is 1. You'll see what I mean in just a minute here. Hang on. So I want to linearize it. So I'm going to put the L over here. I'm going to put what I've got to work with. L of x is equal to f of a plus f prime at a times x minus a. What the heck is a?
1. X. Yeah. Or x is 0.
Hang on just a second. What does this graph look like? Do you know? Can you tell? Based on what you know about transformations? I saw a couple of hand drawings, but where does it start?
-1.
Yeah. So let's take a look and see if we can see graphically what's going on. If I go back here to -1, it opens up like that, right? And I wish to figure out what the value of f of x equals 1 point. This is what I'm ultimately trying to do, is find f of, I'm trying to evaluate f of x for the square root of, well, no, I'm just trying to evaluate whatever 1.02 is using a line. I want to know what this is. Take a look at the instructions so that you can kind of doing this piecemeal. Take a look at it. It says find the linearization of this function 1 plus x square root at x equals 0. So they're telling us the value they want us to look at, and use it to approximate the square root of 1.02 without a calculator. And then we will use the calculator to test its accuracy. Okay. So what we're saying is at x equals 0 right here, we want to use that line to evaluate the 1.02 as starting at x equals 0. So that means that a equals 0. That's what we're saying. Okay. And by the way, if a equals 0, then f of a equals 1. Take a look. If I put 0 in there, I put 0 in there, square root of 1 is 1. Okay so far? Now, because I'm running out of space here, I also need this. I need to evaluate f prime at a. So I need the derivative. What is f prime of x?
1/2 square root of 1 plus x.
That seem reasonable? When you square root, when you take the derivative of the square root of something, that's 1/2 root that times the derivative of the inside, but in this case it's 1.
Right.
You following me? This is f prime of x. Then what is f prime of a? So up here, f of a was what? 1. What was f prime at a? 1/2. What was a? That's a very nice line. That's a lot easier to plug things into if you're close to the point of center. That's a bad way to say it. Center point, which is the point. This is our center point, 0, 1. That's where we're going to go. So we're drawing the tangent line right here, and we're going to use that to evaluate the derivative of 1.02. Sorry, the square root of 1.02. So if this is L of x, this is the equation of my tangent line. Do I plug 1.02 in for x?
Yes.
No, you got to be clever. Look at the original function. If I want to evaluate the square root of 1.02, what must x be? 0.02. Okay, so L of 0.02 is how I'm going to approximate this. I'm going to do the line that belongs to this near the center point because 0.02 isn't very far from 0. So I'm looking for the linearization right there, and that should be awfully close to the actual value of the square root there, the square root of 1 plus x. Are you following me at all?
Yes.
Okay, so if I find L of 0.02, I'm going to get half of 0.02 plus 1, and that's easy arithmetic. That's 0.01. Do you see? Now, what is the square root of 1.02? 1.099?
0.9.
Keep going.
1.0099.
Oh, 0099.
5.
Pretty darn close, right? Leave that in your calculator, Kyle. How far off are we? Do you know how to figure how far off something is, percentage-wise? Yeah. You take the approximation minus this, or this minus the approximation. Either way, one of them's going to be negative, one's going to be positive. Same size number, right? You take this minus this, because this is already your calculator. So you just go answer minus this. And what do you divide by to figure out the percentage off you are? You actually divide by what it actually is. So to figure out how far off we are, after you figure this out, calculate this, you get this new calculator, you say answer, put it in parentheses, minus 1.01, our approximation, divided by answer. And it will use that answer twice, here and here. And that's what you do. You take the actual minus the approximation and divide it by the actual, and what do you get?
Like 0.0000049. 4.9 e to the negative 5.
Good. Okay. So this is what you get if you want to make a percentage out of it. You get it right there. And that's still 0.005%. That's really accurate. But the reason it was is because we weren't very far from the point. 0, 1. That thing wasn't. And so we expected it to be awfully close. And that's the key. You got to stay close to this point of centrality. Now, you might be thinking, okay, well, that's great, but this was a big deal in the old days when nobody had a calculator. If an approximation would do, linearization was a big deal. It's not such a big deal anymore. So why are you learning it? Because ISU says you have to.
Yes.
Nobody linearizes things anymore to get a problem solved. You're going, why do we have to learn it? Because it'll be on the final, that's why. And that's a horrible reason, but it's a reason. And it's awfully cool to look at the historicalness of it. And you're going, yeah, I can appreciate the history of it. That's really cool that they came up with these tools, but I don't have to use them anymore. Yes, you do. Because you have to pass the test. Right? Yeah. All right. So yes, it's a fact. It's a process that I'm supposed to teach you, and that's what we're doing. Let's try example 2 and see if we can do it again and get it going a little bit faster. I'm going to leave this linearization formula up here. By the time you're done with the exercise, you better have it memorized. You may have it already because it's just our line. It's just written with calculus notation. That's all. So, example 2 says, find the linearization of f of x equals cosine x at x equals pi halves. Okay, let's do that first. So our function is cosine x, and our a is pi halves. Okay? In order to write that linearization, I need two things. I need to know what f of a is, and I need to know what f prime of a is. So I'm going to put those things in a list. So what is f of a? In other words, what is f of pi?
Oh, that's 0.
Yep. Cosine of pi halves equals 0. What is f prime of x? I want to find that first.
Negative sine x.
Negative sine x. And now I want to find f prime at a, which is f prime at pi halves, which is negative sine of pi halves. And what is that? Negative 1. Good. So now I'm ready to do my linearization. L of x for this problem is going to be f of a, I'm not going to write, plus f prime at a, which is negative 1, times x minus a. Catch all that? Okay, that's my linearization of x. Here's what I want to do. I want to find out what's the, so I got my linearization, that was the first thing, and use it to approximate the cosine of 1.75 without a calculator. We're trying to approximate, like we were trying to approximate the square root of 1.02 before, now we're trying to approximate the cosine of 1.75. That's what we're trying to use this to approximate. So what is x?
1.75.
It is. Because look, here's your function. So it is. What you're plugging in right there, that is x. Before, we had to go 1 plus 0.02. And we got 0.02 for our x, remember? But this one actually is what we're trying to cosine. And so we're trying to find L of 1.75, which is negative 1.75 minus pi halves. Now, most people in the old days knew what pi halves was, at least to the nearest hundredth. Do you? 1.57.
Yeah.
So what is 1.57 or 1.75 minus 1.57? I'm trying to do this like the old days without a calculator. 15 minus 7 is? 8. And we borrowed 1 from there. 6 minus 5 is?
1.
So we have negative 0.18. Is that correct? What is the cosine of 1.75? I want to find the error. We found our approximations right there. That's approximately the cosine of 1.75, I think.
Wait, where did you get the 1.75 again?
That's negative 0.7.
It's about 0.02 off.
Give or take. First, I thought that.
I was like,
I understand. Are you okay on that, Bailey?
Yeah.
Where we got it from? It was in the stem of the problem.
okay, I was looking.
We could be a little more accurate with this. Does anybody, I mean, we could have taken 1.75 minus pi halves in our calculator. However, we were asked to do this without a calculator, so we have to know what this is approximately. So I'm going to go ahead and go with this because we're supposed to do without a calculator. This is what I get. It's not negative. Oh, yes, it is. It's negative. Okay. And so what is the cosine of 1.75 according to the calculator? Make sure you're in radian mode.
Negative 0.178.
Negative point what?
178.
Okay. To figure out our error, I want you to take what it actually is, which would be answer, in parentheses, minus, actually plus, because it's minus a negative, right? Right?
Yeah.
And divide it by answer. This being the answer.
Oh, it's the negative.
Do y'all see how you're going to check your error? By using the line to approximate. Do you see how we're going to check the error? We're going to take what it actually is according to the calculator, minus what we got, and divide it by what it should be. And what do you get?
Negative 0.0098.
0.0098. Okay, so that one is a little less than 1% off. The negative doesn't matter. It doesn't matter which direction you're off of. Okay, so that one wasn't as great. Still awfully close. If you can tolerate a 1% error, this was a heck of a lot easier to plug in than this would have been to look up on a table or to interpolate from a table. And that's if you have a table. A lot of times people have to generate their own tables. People used to pack around books like this around college campuses because a lot of stuff had been figured out to 4 decimal places because they didn't have a calculator, they didn't have the electronics. Look at this book. Look at those tables.
So helpful.
You wanted to be an engineer or a mathematician, you packed around one of these and a slide rule. Looked like you were armed with a short dagger everywhere you went around campus, because those slide rules were about this long. You want to see one?
Yeah.
So this was the old days when they even had tools like this. When you were in Newton and Leibniz's time, they didn't even have that. They had to figure out everything from scratch every time. I bought this off of eBay. Nobody uses them anymore. But you take a look at this sometime. I don't know how to use it. I wish I did. It'd just be fun historically to do. I would never use it. But it was like a calculator. And this one, there's a hairline line, right? Just a hairline. You get it lined up with a certain way, you could read it to up to 4 decimal places of accuracy. You could do logarithms, trigonometry, all kinds of things on this. It's a slide rule. You used to put it in a little case like this, and it used to have obviously it's busted. Put a little belt loop through there, and all the engineers and mathematicians walked around like this around campus with their stuff, okay? Because that was the tool they had. Now you guys walk around with this. You don't show everybody because you don't want to be classified as a nerd, or maybe you do. I do. But this has become your tool. But these are the old ways, and it's worth understanding the trouble and the cleverness of the old ways. Do you have to practice it? Yeah, you do.
Did they use power series?
What's that?
Did they use like the infinite sum things? Suggesting that's not common thing.
Who's asking you something?
They use infinite sum things.
They use what in something?
The infinite sum things.
Oh. Infinite sums. To approximate things?
Yeah.
Yeah.
How they got those things.
Yeah, you're right. You're right. Infinite sums. I had to recall where that came from. Okay, we'll leave that up there. Okay, take a look at example 3 now. Example 3 has a special case. A special case that you're going to have to be able to manipulate. It's kind of fun to do if you're reasonably good at algebra.
Oh,
Not so fun if you're not, but they won't give you ones that'll kill you. Just make you sick. Okay? This is what they're claiming in example 3, that 1 plus x to the k. So it's a binomial with a 1 here. This is important. It has to be 1. This could be a plus or minus. This could be a lot of different things, but this has to be a 1. And that's where your algebra skills come in. To the k is approximately equal to this line, 1 plus kx. Can you see that this would be a lot easier to plug an x value into than this one?
Yeah.
Especially if k is something like 10. K would be 10. Just 10 times x and add 1. But this is approximately equal to this. This is the linearization of this. This is the line that belongs to this powered binomial where there's a 1 right there. Do you want to see that linearization developed?
Yes.
You do?
Yes.
All right. So f of x. Oh, by the way, one big, huge, monstrous thing I forgot to tell you. Listen to this. It says applies to powers of 1 plus x for small values of x. And that means that x has got to be really tiny. Can't get very far from 1 plus x. I'm trying to find the thing that I forgot to tell you. I'll see if it's on there. Oh, yeah. Here's what it says, right? It's very, just before they give you the ABCD, it says, use this formula to find polynomials that will approximate the following functions for values of x close to 0. That's the operative thing, close to 0. So what do you suppose our x value of our center point is? 0.01. 0. You can't vary very far from 0 using the linearization. So that means our center point, or the point of tangency, we're going to draw our line to approximate, is going to have an x value of 0. Can't let x get far from 0, so we're going to let it be 0 to do our linearization. Okay? So linearize this right here. If f of x is equal to 1 plus x to the k. This is really good. This approximation is really good so long as this stays close to 0, which means that A is 0. So what is, that's the next thing I got to find. What is f of A, which is 0? It will be 1 plus 0 to the k. And what is 1 to anything? 1. Okay, so that's our f of A is 1. What is f prime of x?
Plus kx.
K times
And 1 plus x to the k.
1 plus x to the
K minus 1.
k minus 1 times the derivative of the inside, which is 1.
Yep.
This is the derivative. What is f prime of A? K times 1. If x is 0, I don't care what this turned into. 1 raised to it is 1.
Yep.
So it is k. You with me here? So that means our linearization is going to be, for this function, is going to be f of A, which was 1, plus f prime of A, which was k, times x minus A, which is x. Because A is 0. So it is kx plus 1. Or 1 plus kx. So this is the linearization for any binomial, well, 1 plus something, raised to any power so long as this something is close to 0. Reasonably close. This is an approximation for it. The line that goes with, this is the tangent line that goes with any polynomial of this sort, near 0. Which was a useful thing for a lot of things people did. Now here's how you can play with it. So we're going to use that fact, now that we've developed it, we're going to use that fact and we're going to say, use it to do the cube root of 1 minus x. So this is going to become 1 minus x to the 1/3. Is that okay? Because it looks more like this. I changed the cube root to this. It's the cube root of 1 minus x. And we're claiming that that is equal to, approximately equal to this, which would be what in this case?
1 minus
1 minus
1/3 x.
1/3 x. That's the k. Catch that?
The negative came
I'm only getting a nod from Brent. That's it. Well, Landon's throwing his head around now. He's going to do brain damage in a minute.
Where did the negative come from?
The negative, because it's minus x, so it's minus. And then another 1/3.
Okay. That's not too
It's
bad.
minus right here.
Yeah.
So it was really, what it really was, if you really want to see that it corresponds to this, is 1 plus negative x to the 1/3. There's your plus sign. And this, whatever that is multiplied by 1/3. Yes.
So on the linearization on the right side, why do we get f prime of x if we don't use it in that equation for the f of a?
We did. It just whittled down to this. This is f prime of x. This is f prime of 0 because we're centering things at 0.
I'm talking about like in the top part because there's no f prime of x directly in there.
Yeah, it's just k.
F prime at the center was just k.
Yeah, f prime. I'm talking about the f prime of x.
Yeah, there is no f prime of x in the linearization. There's f prime evaluated at a. So I found f prime of x as a general rule here, and then I substituted x equals 0 in right here and came up with k.
Oh, okay.
Because I'm centering it at 0. I needed to find f prime at the a value we're centering it on.
So you have to get f prime of x so you can get f prime of a.
Right, right. I had to get f prime of x so I could get f prime of a. You okay with that?
Yeah.
Everybody good? Okay. So this is the approximation for this one. If we use this approximation, this is how we apply it here. Let's plug it. We good? Let's try the next one. So we're going to leave that up there. And the next function I wish to consider is 1 over 1 minus x. Do you understand that that is this?
Yes.
That's the trick, is to write it with an exponent where k is, so you can tell what k is. What is that approximately equal to using this from here to here, what would that be?
1 plus X.
1 plus X, because it's negative 1 times negative 1, which is positive 1 X. Yeah? We good? That one wasn't so bad, but you have to what's going on. The next one is the square root of 1 plus 5x to the 4th. Would you buy that?
Yep.
Okay. The part of this side is that it'd be 1 plus something. It doesn't really matter what the something is to apply this. So what will the approximate value or the approximate linearization of this be?
1 plus 5
halves.
halves. 1 plus 5 halves x to the 4th.
Not too bad, right?
Yeah.
Okay, the next one is 1 over the square root of 1 minus x squared.
Oh.
1 over the square root of 1 minus x squared. So it would be 1 minus x squared to the negative 1/2, which would be 1 plus 1/2 x squared would be its linearization.
Yeah.
Does that make sense to you? Okay, now, every one of these 4 examples has always had a 1 right here.
Yep.
Not gonna happen in the exercises.
But doesn't it have to have one? So
It
that's
does.
where the algebra comes in, right?
Yes, where the creative algebra comes in. This has to have a 1 right here, and if it doesn't, you gotta come up with something creative to force this to be a 1. Generally, it involves factoring something out.
Yeah.
And it gets, yeah, I gotta get creative with it. But this is, you're gonna be using this fact. I doubt you'll be tested on it, at least on the final exam, because it's kind of an obscure little thing. But you may be tested on it on the next quiz, probably. Maybe the test at the end of the chapter. So you're gonna need to know this, at least to get past a quiz and a test. Okay? Moving on. Let's look at example 4. We're gonna do some more arithmetic using square roots, because that was a very difficult thing for people to do in the old days, because they didn't have a calculator. There was an algorithm, you know, the division algorithm, where you take what you're dividing by, you stick it out here and you put in here what you're dividing here, and then you have a method for getting that done by hand. They had a method, a pencil paper method for evaluating square roots to as many decimal places as you would like. And it's the most obscure, strange, bizarre thing. I've seen it demonstrated one time. Never learned it, because I always had a calculator. I'm at least not that old, but I'm old. But I've always had a calculator from high school math on when I needed one. We've had electronics, at least that one, but not one of these. When the scientific calculators come out, like the little TIs, the solar powered, they're only $12 now. Those are all the rage. It'll be interesting to see what's all the rage for your kids. All right. Square root of 123. We want to use a linearization to approximate the square root of 123.
Oh,
You're going, what are we going to linearize with that?
the derivative is 0.
The derivative is 0. The function, folks, the function that we're trying to use is this one. Right? Where do you suppose we should center it?
0.
Because they aren't telling us that now. Where should we center this to approximate? Here's what I'm saying. We got a graph like this, which is square root's coming out like this, and it keeps getting bigger and bigger and bigger. Somewhere out here at 123, I want to approximate this value.
121.
121 would be great. I realize this is an exaggeration,
Why 121?
because it's a perfect square,
Oh, that
which we
makes
can square root. Okay, so I come up to here. This is where I would center my tangent line, and look at this tangent line by the time we get this far out. I mean, it's very, very, so close that you probably can't tell the difference. Using this to approximate this can be really good. We center it at the closest square, because we can square root 121. You following that? Okay, so we centered it at 121, which means that A is what?
11.
A is 11?
A is 121.
A is 121. And f of a would be 11.
Yeah, that works nice.
And f prime of a, I need to find f prime of x first. What would be f prime of x for this?
1/2 x to the.
1 over 2 root x. And f prime of a?
1/22.
Yes, right, 1 over 22. That's the slope of that tangent line when we get clear out here. It's pretty shallow. Y'all follow what we did? If we're trying to approximate a square root, then the square root is the function. Find yourself a square root that is, the square root's evenly, really close to this, and center it there. That's what your a is going to be. That's what you have to decide. Then you got to find f of a and f prime of a to use the linearization idea, which I erased over here. That would be L of x would be what? Have you got it memorized yet? 11 plus 1 over 22 times x minus 121. Now this is going to take a little more effort. It's not going to be quite so simple. This will be 11 plus 1 over 22x minus 121 22s.
Yep.
Yeah.
11 comes out of both of those and reduces to what?
11 over 2.
11 halves, right? It doesn't?
Yep.
Yeah, there's an 11 times an 11 and an 11 times 22, and so it leaves 11 over 2. What is 11 minus 11 halves?
11 halves.
Yeah.
Oh, nice.
So let's just 22 halves.
There is our linearization. Where do we evaluate it? If I want to approximate the square root of 123,
121.
123.
yeah, look, this is your line. This is your line that's tangent right here. We want to evaluate that line at 123. That will approximate it for us, right?
Right.
Okay, so I'm going to do L of 123, and that will be 11 halves plus 123 over 22. And they were very good at fractional arithmetic. I'm going to take that back to 121 over 22 so I can add it.
I see.
244.
Yep.
I'll keep doing it without a calculator. They were very good at this. What am I doing? Oh, 22. And then 2, and then 0. So that will be 0. And then 200. I don't know. But anyway, it's going to be 11 point. Give me one more. How many times 22 going to 200? 8? 9? 9 times? Okay, and 9 times 22 is what? 198. So I get another 2 here, so it's going to be 999, right? Isn't it? Is it?
9092.
909090? Oh, yeah, you're right. So it's repeated from here on. So what is the square root of 123? 11.09205. So we're not off until we get to the thousandths place, and it's not off by much.
No, it's after the second half.
What?
It's 0905.
090, right here is where it's off.
Yeah.
So in the 10,000ths place, pretty good approximated. But we would expect that, knowing what we know about the square root curve, way the heck out here is practically flat. So the curve is practically the line there. So the line's a great approximator for it, especially way out there. Now, what about the cube root of 123? I got to stay on this board. What about the cube root of 123? What's our function?
Cube root of x.
What's our center? 125. That's the perfect cube closest to that.
Yeah.
So we'll say A equals 125
code find this one. 25.
So what is f of a?
5.
5. What is f prime of x so that I can plug something in? It's 1/3 times x to the negative 2/3, right?
Yeah.
Which is 1/3 cube roots of x squared. If you change it to that notation, you could leave it like this, or you could leave it as 1/3 x to the 2/3 if you prefer. That's okay too. So what is f prime of a, which is 125? Plug it into there or there. Don't use your calculator.
I definitely didn't.
I think it's like around.
Look what this means. Just listen to me a minute. If you cube root 125, that's what that indicates right there. Is you're going to cube root 125. You get 5, right? This says take 2 of them.
Square it. Yeah.
2 times 2.
What if we tried to square it and then cube root it?
Then you would square root it and take 3 of them and multiply together. You do this to the number, which is 5. Then you multiply this many of them together.
Number is 5?
Yeah.
Yes, the cube root of 125 is 5. That's what I'm doing. Cube root of 125 is 5. Now take 2 of them, multiply them together, you get 25. 3 times that is 75. So our slope is 1/75. And they were, in the old days, clever like that because they had no calculator. They didn't have a crutch. They weren't weak-minded. They just had other methods, people. So what's the linearization of x? 5 plus 1/75. Okay, so now we got to do some arithmetic on this. Shh. 1/75x. What does that reduce to, do you think?
125/75. 5/3.
Take a 25 out of both? Yeah. Okay. And 5 minus 5/3 is? 10/3. I may come back to mine if I need to combine some things. That's what my linearization is. Where do I evaluate it? At 123. Remember? That's our line. We want to evaluate the line at 123 rather than the cube root function. Right? Okay, so I have 10/3 plus 123/75. So I'm coming back to this. How do I convert that to 75s? Multiply by 25, so this would be 250/75 plus 123/75, which is what? 373/75. And then they would do this, but they were very fast at it. Okay, it doesn't go into 37, but it goes into 375. Oh, brother, 75, 350, twice? No, that'd be 150. 5? Oh, 373. Yeah, it's too high. Okay, so how many times? 4? 4 times 75 is 300? Nine times 75 is what? 725?
No, wait. 9 times 75 is 675.
Is it?
That's right.
Okay. And that difference is 55. Bring down another 0, 550. 75 into 550 is what?
7 times.
7? Is 7? And 7 times 75 is? 7.
525.
525?
Yes, 25.
That's 25. Give me just one more. 75 into 250? 3, I'll stop there. That 3 times 75 would be, what, 150, 225? So it looks like it's gonna be 3 repeated, is that right?
Yeah.
All right, so now, take the square root, or the cube root of 123, tell me what you get.
About 4.973. 1.
1/8, this would have been 3, so it's off in this place right here. Not by much, pretty good, okay? So that's old day approximations to get things moving along. Now, Newton's method is next. And I'm going to give you the concept of Newton's method. And if you wish to study the details, the procedure for Newton's method is on page 236. And if you wish to learn it, there will be bonus points available to you on the quiz and test for Newton's method. But I'm going to give you the concept. And again, these guys that didn't have the electronics as a crutch were extremely clever. I do not like Newton as a person, but boy, was he brilliant. He was a tremendous physicist, and he knew the math and could invent the math that he needed to do the physics he wanted to do. He was incredible. Yes.
Why do you dislike him?
Because he was a stuck-up brat, reclusive, didn't talk to anybody. And if you couldn't understand what he was saying, you weren't worth talking to. I don't like people. Okay, moving on. Newton's method said this. Newton's method was a totally different way of doing something that your calculators do. And they may even use an algorithm involving Newton's method to do this, your calculators. But if you got a curve like this, whoops, I don't want that. It's got to cross the x-axis. So you got a curve of some kind that crosses the x-axis here somewhere. Maybe right there. And you are looking for this 0. Today, we've got polyroot finders. We've got the quadratic formula. If it's a quadratic, if it's a cubic or a 5th power, heaven forbid, we don't have a method for finding zeros. We have a way of approximating them. And I'm going to show you Newton's method. What he would do is he would take this curve. Sorry. I'm just going to try to make it heavier. I'm going to make it a little bit more roundy. He would take this curve right here and find a point on it. That was pretty easy. If you were clever and you could plug in an x value somewhere near this, approximately, anyway, say right here, and it was an easy plug-in, he would find that point right there, find the equation of the tangent line there, which is our linearization, whoops, find out where that line, find the 0 of that line where it crossed the x-axis, plug that value into the function, find the tangent line equation there, find out where it hit the x-axis, take that one, plug it in, find that tangent line until it got close enough to the actual 0 that, and then you're going, how do you know how close he got? Because he could see it on, he would graph these things by hand. And he would figure things and he knew about where that 0 ought to be. And it's called error analysis. He was good at that too. I don't want to get into that. But that was really clever. Find that one, go up, find that tangent line, and the tangent line just keeps winding down until the tangent line hits the x-axis in the same place the curve does, or pretty close. That's clever. And there's a method. It's called iterating. You keep doing the same thing over and over and over again. You find an x value, you plug it in, you find a tangent line. You find an x value, you plug it in, you find a tangent line. You keep going like that and do as many iterations as you would like until it's gets you to 6 places of action. It doesn't take very long, but the procedure is in the blue box. And that's all I'm going to say about that. You can see some examples of how it's used, especially example 5. But I'm not going to talk to you about it because it actually doesn't require me to teach you Newton's method. I just wanted to show you it's very clever. Very cool. So now the other things that I need to teach you from recording to ISU, I'm cutting out this entire page and a half here. I need you to go to the bottom of page 237 where the big word is differentials. Remember I told you if I was going to title this chapter or section, it would be linearization and differentials, introduction to differentials. Well, here comes the differentials. And I'm going to get as far as I can today, but I won't get completely done. We'll talk about them a little better tomorrow. Differentials are far, far easier to use and understand than the linearization. So if you were okay with linearization, it was a little bit difficult, this is going to be super easy for you. All right, so a little bit of blurb here, historically talking. Listen, bottom of page 237, don't go to sleep on me. Leibniz, one of the inventors of the calculus, used the notation dy over dx to represent the derivative of y with respect to x. You see that all the time. The notation looks like a quotient of two real numbers, but is really a limit in which both the numerator and denominator go to zero without actually arriving there. Remember the reason why I use little d instead of capital Greek delta? When you see delta y over delta x in physics, it means a bigger change in y. It's like the secant law. When you use little d, you're using the definition of tangent. It's actually a limit. Go back to the definition, okay? That makes it tricky to define dy dx as separate entities. Leibniz, and see this side margin, Leibniz and his notation? Since we really only need to define dy and dx as formal variables, we define them in terms of each other so that their quotient is derivative. But they are still separate things. It's the change in y per the change in x. They're very tiny changes. So, think about this. This is really easy to understand. We don't get into too many details. dy dx means the derivative of y with respect to x, right?
Yep.
We also write it like this, f prime of x. They are equivalent to each other.
Yep.
Which means that if we treat this like a quotient, the change in y is equal to the derivative of x times the change in x. Cross multiply, that's it. These two pieces of this quotient taken individually, this is called the derivative. These pieces are called differentials. This is the differential of y, this is the differential of x. And dx is a differential, dy is a differential, and these two statements are equivalent. Okay, that'll be useful to us here in just a second. Example 6 says, finding the differential dy. It says, find the differential dy and evaluate dy for the given values of x and dx. So the first one we've got to do is y equals x to the fifth plus 37x. That's very strange. Y equals x to the fifth plus 37x. If we are going to use this right here, then dy, think about this. I'm going to do it all at once. It's not a difficult thing. Well, maybe the first time I'll do it this way. dy dx would be equal to 5x plus 37. And dy, the differential dy would be 5x to the fourth plus 37 dx. That seem right? Okay, so on this function, it says, find it when x equals 1 and dx equals 0.01. That's not hard.
So that's 5 plus 37, it's 42.
The change in x is just 0.01. It's moving to the right just a smidgen, 100th of a value. What's the change in y as we move to the right? Just 100th. On this curve, if we move 1/100th from the number 1 on this curve, whatever it looks like, a fourth degree polynomial, if I find the point 1 whatever on the original function and I move just a smidgen to the right, what will that result in for the change in y? That's what we're looking for.
From the derivative, why not the original?
Because we're using linearization still, we're using the line
Okay.
to approximate this. So anyway, so it's going to be 5 plus 37, right? What is that?
42.
42 times 0.01? 0.42. So in the curve, x to the fifth plus 37x, whatever that curve is, when x is 1 and we move to the right of 1 on the curve, just a little bit, it results in a change in y of 0.42. So you move to the right a penny, you get a change of 42 cents in the y, basically. That's comparison-wise. You get a pretty big change in y for a very small change in x in this curve when x is 1. That's what we've discovered. Okay? The change in y with the given change in x. And it requires, and it comes from this function, or this definition right here. You have to find the derivative of x and take it times dx for them to be equivalent. That's another explanation, Landon. Why do we use the derivative instead of the function? Because this is the slope, the tangent line. Okay? And we're not going very far from the center point. Okay? All right, let's try the next one. Sine 3x at x equals pi with a change of negative 0.02. What's dy? What is dy? The cosine of x dx. Where are we centering it? What's the x value? At pi? What's the cosine of pi? -1. What's the dx? Negative 0.02, right? What's that product?
Negative 0.02.
0.02. So guess what? On the curve sine x, if you deviate to the left of pi, 0.02, you get a change in y of 0.02. So that means that the line there's got a slope of -1. Okay, let's do the third one. X, oh, this will be a tough one. Because it's got to be derived implicitly. It's not that hard, but we can do it. We can do it. What's the original function? Or it's not even a function. What's the original relation?
X plus y is xy.
And we have to find the differential dy. And when we find it with that differential, we will evaluate it when x is 2 and dx is 0.05. We got to find that first. So we got to find dy dx. And because it's written in terms of x and y, we got to use implicit differentiation, and we got to use the product. What's the derivative of x?
1.
What's the derivative of y?
dy dx.
How do I apply the product rule? What do I get? X dy dx plus y, right? Okay, I've got 2 dy dx's, so I'm going to take dy dx out, and I'm going to have 1 right there, minus x equals y minus 1. Did I do that too fast? No. Then dy dx is going to be minus 1 over 1 minus x. Can I do this to you? Based on what we just learned? Okay. So we're going to plug some things in. They want us to evaluate it when x is 2 and dx is 0.05, but we got a problem.
Y.
How are we going to find out what y is?
You're just gonna plug it in the original.
Plug it in the original. Exactly. So we got a little bit more work to do. X is what? 2. So I have 2 plus y equals 2y. Right? Plug it in here, you get 2 minus 1 over 1 minus 2. That's -1. Times dx is, I don't know what it was, 0.05? So we get a drop of 0.05 in this function when we move to the right, 0.05. We drop the same amount we went to the right at that point. Okay, we'll continue tomorrow. You have plenty of information to get started on this assignment, so get after it. We'll finish this tomorrow. This one.